Okay, in this video we're going to look at half-life. So all radioactive substances decay exponentially, among other things as well, not just radioactive things. And as they decay, they have what's called a half-life, and that's the time required for half of the substance to decay. So let's take a look at an example. Let's say a scientist begins with 250 grams of a radioactive substance, and after 250 minutes, the samples decay to 32 grams. Okay, so it's lost more than half of its weight in 250 minutes. Rounding to 5 significant digits, what we're going to do is write an exponential equation representing this situation in other words, a model. And then to the nearest minute, we're going to figure out the half-life of the substance, which will obviously be less than 250 minutes because somewhere within that 250 minutes, it went from 250 grams to 32. So half of 250 is 125. So we're going to try to figure out how long does it take for this 250 grams to decay to half of its original amount, or 125 grams. Okay, so in order to do that, first we need a model, an exponential decay model. So I'm going to call it P of t. You can really use any letter. P of t for the amount. A lot of people would call it capital A of t for amount. And that equals the initial amount, which I'm going to call little a, times e to the RT, where R is the decay rate, E is the Euler's number, and A is just the initial amount, or the coefficient out front. So we know that the initial amount is 250, so we can go ahead and plug that in. Now we don't know the rate at which it's decaying, but we do know that after 250 minutes it's decayed to 32 grams. So what we can do is plug in that point to solve for the rate of decay. So we have 32 is equal to 250 times e to the r, and t is 250. And you do want to do a quick double check at this point to make sure all of our units are correct. It looks like in all of the numbers given in this problem, everything is in grams and minutes, so we don't have to convert to hours or anything like that. Okay, so next we can solve. So we're going to first divide by 250 to get that out of the way. So 32 divided by 250 is equal to e to the 250 r. And we'll take the natural log of both sides. So we have the natural log of 32 over 250 is equal to the natural log of e to the 250 r. And then over here, those cancel. So we get 250 r is equal to this. So I'm going to go ahead and divide both sides by 250. So r is equal to the natural log of 32 over 250 all over this 250 right here. Since this is equal to 250r, so I'm just dividing by 250. And we need a calculator here. We're going to round to, it says 5 significant digits. I'm just going to round to 5 decimals. It's going to be close enough. So 32 divided by 250. And then we're going to take the natural log of that and then divide that by 250. Okay, so r is equal to negative 0.0, actually we do need 5 significant digits, it's 0.00822229, so those are our 5 digits there. 0.00822229, and r is negative and it works out naturally that way since this is a decay problem. Okay, so then our model, we can put it together, is P of t is equal to 250 times e to the negative 0.00822229 t. Okay, then it says to the nearest minute, what is the half-life of this substance? In other words, how long does it take to decay to half of its original amount? So what we're saying is we want t when P of t is equal to 125. So if we plug in 125 for P of t, we can solve this equation for t. So when we do 125 divided by 250, that's a half, 0.5. And then we take the natural log of both sides. And when we take the natural log of this side, I'm going to go ahead and skip ahead to what it will simplify to, negative 0.0082229t, just that exponent, and then divide both sides. So we get natural log of a half divided by r. Okay, and it's always going to work out that way, whether we start with 250 and we decay to 125, or maybe we had, let's say if we started with 32 and we were asking how long it would take to decay to 16, half of 32, right? We would still, when we divide 32 by 16 at this first step, we'd get a half, we'd get this exact same equation, and we get the exact same answer. So the half-life, it's really the time required for half of the substance to decay, and that doesn't matter at what point you look at it. At any point where you look at it, you say how much longer till half of this is gone, it's always the same amount of time. And let's see what that time is. So we have this number here, which I want to put in the denominator, so I'm going to do 1 over x, and then times this numerator, natural log of a half. Actually, hang on, I'm going to have to re-enter that. That's going to be easier to just clear and type in the other way. So let's do 0.5, take the natural log of that, and then divide it by, and I'm just going to type this in, 0.0082229, the negative. And so we get 84.295. I can't write here. 84.295 is what we're looking for. There we go. Minutes. And the question is to the nearest minute, so you just round, about 84 minutes is the half-life for that particular substance. Okay, looking at one more example, the half-life of Ebrium-160, that's just a radioactive substance, is 28.6 hours. Okay, so in this one we're given the half-life, and it says what is the hourly decay rate to 4 decimal places, or as a percentage to 2 decimal places. Well, let's actually go back up to the previous problem here and take another look at it. So what we've got right here is that the half-life is equal to natural log of 1/2, or 0.5, divided by r, and that equals the half-life, and that's true for any substance. So we could use this fact to make answering this question much more quickly. Okay, r is the decay rate. So if we know that half-life is equal to the natural log of 1/2 divided by the decay rate, and we're given the half-life is 28.6, well then we can plug that in and solve for r. So r is equal to the natural log of 1/2. I'm skipping a step here, but if you multiply both sides by r and divide both sides by 28.6, we will get this. And let's see what that comes to. So 0.5, take the natural log and divide that by 28.6. We get negative 0.02423. Actually, negative 0.0242. We'll go with that. Okay, and then as a percentage to 2 decimals, we would move the decimals over twice, so that would be 2.42%, and we are in hours, so per hour. So that's how much is decaying per hour. And then after 28.6 hours, you've lost half of whatever your initial amount is. So that is it for half-life.